Hello everybody, this is a short update on my video number 3, a question to flat earther about downward acceleration versus latitude. And I see from the comments that some people don't understand what I'm asking for and what this data is actually. So I clean up the spreadsheet, made it a little bit bigger, and here I only show location using longitude and latitude, but also city names where the measurements were done. If you don't accept these locations, you can introduce any own frame of reference or coordinate system. This is height above the sea level, and this is measured acceleration with references to different data sources. And what is this acceleration? I will not use the word g because some people were triggered, and this is the entire point of this video. I don't claim, for the purpose of this video, I'm not claiming any mechanism for this acceleration. It is there, and it is changing depending on the location, okay? And if you take this data, there is some correlation between some of this data, especially latitude and height versus acceleration. However, maybe there's some other reason. But how this is measured? I looked at about 20 different sources and checked what equipment were used. So in all the ones I checked, a free falling reflector was used to, reflector was lifted up by a motor or a lift, and then it was dropped. It was released in a vacuum tube, and shortly after release it will be just free falling. It will be accelerated. It will not be moving at the constant speed. It will be going faster and faster until it reaches the bottom, where it will be catched by some bed and some springs, and then automatically it will be lifted again. Lift will go down, it will be dropped, and it will be dropped again, and it can be repeated for many measurements. The tube is a vertical tube with vacuum in it, so the effect of pressure and air density and drag is not a factor. um, This is to improve the accuracy of the result. If the vacuum will not be there, there will be a slight effect of pressure between different measurements. And this is not what this acceleration, this is not what we want to measure. So this is why vacuum is used. If the vacuum would not be used, you will still get result which is pretty close to this data. However, the machine will be needed to be redesigned to deal with the drag, which could be different in different conditions. The moisture can get in, the air can get in, and then you will have a mess, and these values will not be as accurate as they are here. However, they will be close, and you will still see the acceleration changing depending on position and height too, but the height will not have significant effect or pressure. So how this machines operate? They are commonly called gravimeters, but fear not, they don't measure gravity really. All they measure is a speed and velocity and acceleration of a free falling object. Here is an explanation of very classical gravimeter. Again, this is, I will call them accelerometers, okay? Because this is what they actually measure. The absolute accelerometer is similar in concept to all modern accelerometers. The motion of a test mass free falling in a vacuum is interferometrically measured with respect to stationary inertial reference. What they mean is the machine is on the ground, it's bolted on a solid block of concrete, it's not moving. And what we are trying to do is, yeah, drop this test mass. It's free falling. We can measure the distance, we can measure the velocity, we can measure the acceleration. These machines don't really care what is the source of this acceleration. If you, for example, drop this machine from an airplane or in a drop tower, and then once it's falling, you enable it to measure. It will measure something, as long as this motion test mass doesn't hit the walls of the accelerometer. But if you drop it vertically and it stays oriented, and it goes down, it will measure something. And well, you can imagine it will measure 0. If you instead, let's say, attach this machine to a rocket or to a car or to a lift, and you start maybe on a base in a basement of the building with a long elevator that can go very fast, and you, let's say, bolt this machine to the elevator and this measuring machine, and you go up and start speeding up the elevator up. All right, this will be acceleration. And if you then do a measurement, you will get a different result, which will be, some addition of of acceleration that is normally done on the surface of Earth, and acceleration of the lift or a rocket or whatever. Sure. So they can measure acceleration. In all these measurements here, the machine were on ground, not moving. They were on a solid block of concrete. Often the block of concrete will be separated from the building to not introduce vibration. Sometimes it will be in a city, sometimes it will be in a remote area, so there will be no vibration from cars and people and so on. And then, yeah, we can read a little bit more how these things are working. The inertial reference is another corner cube retroreflector mounted on the proof mass, blah, blah, blah. What does it mean? If we look at one of, this is FG5, very popular, and another one is A10 by Micro G Lacoste. This is a very small one, very modern, so it's pretty small. This is the experiment setup. There is a laser on the bottom, a system of mirrors, that there is a mirror that bounces it up. There's a free falling mass with a mirror, retroreflector, that will bounce it back. And this mirror in the middle is semi-transparent, so some light will go down. And then interferometric interference can be measured. And from interference, you can measure the position and the velocity. And from velocity, as it goes down, you measure it million times per second. As this free falling object is falling, of course, and determine what is the acceleration, the number. So this is how it looks, and we'll show you some other ones. This is a bit more recent. It's a bit bigger in control. It's using a little bit different principle. This one is not using a solid mirror. It's using actually it's beam of atoms, but this one is it's a different story. FG5. This is how you call it? A diagram of FG5 accelerometer. And as I said, there's a laser here. Sometimes outside, it is shining through a mirror. It's reflecting up to a drop chamber. There's a free falling corner cube. Then it's reflected back to a mirror here, and then through the main mirror, and then there's interference, and so there's the detector. So this is kind of how it looks. Let's see another. This is the same. This is how it looks in reality. The FG5. This is FG5X. So yeah, here is original FG5. Okay, and we can look at installations of similar equipment here and here as it is installed. This is a different one, different type, and explanation of it. Here's some different installation of FG5. in Germany. And here's another one. This is FG5 and A10, and there's some other ones. Yeah, this is FG5 gravimeter accelerometer user manual. I just wanted to show you how it looks. This is a vacuum chamber. The test mass is going up, then it is released, and it is just sitting on this mirror is just sitting on a cart. Once the measurement is taken, basically this cart is going to be moving down fast, so it detaches from the mirror, and mirror is following it. There is no air, so it will just be following, and then at the bottom the cart will catch the mirror, so the measurement can be repeated automatically. That's one. Here's another very similar image, how it looks. And here's another one. Yeah, exactly the same. Yep. This one doesn't work. There's another picture here, very similar. Here is a different model. It's AMGC-02. But again, it has a different setup. The laser and interferometer system is at the top. And then the launch chamber is, of course, in vacuum. This part goes up. It lifts how you call it, the prism, the retroreflector up, and then it suddenly retracts down. And because there's now no contact between this launch thingy and the prism is going down, right? And it will eventually hit this cone here, catching one. And during this motion, there will be changing distance, changing velocity, and changing velocity. And if you plot it, you can see there's a constant acceleration. What else? This is A10, a bit more modern one. It has a very similar system. There are some pumps to get a vacuum here. Are there any other pictures that are of interest? This is a principle, how it works. You see distances measured at different points. And these are interference patterns measured at photodetector. And they will be changing. And the distance between them in time, which can be measured using oscilloscope and data logging systems, they will be changing. So from these changes, the velocity and acceleration can be obtained. Dropping chamber, travel lock, upper lift, some cables. It has a laser inside, because the lasers got much smaller now than what they were 30 years ago. So this is a smaller unit than FG5. This is another one I found with some examples. This is FG5, serial number 202. This is for reference. And do we have more? This is already what we've seen before. What kind of laser it is used. Okay. What is that? This is a very obvious, this is very well-known equation, right? The position is initial position plus speed plus time, since x0. So this is time from release or some reference point. This is acceleration. This is acceleration. This is the distance traveled due to the acceleration. This is the acceleration value. This is I don't know what it is. This is probably what could this be? Some drag data, maybe. I'm not sure. I'm not an expert on this topic. Okay. This is not important. what is this? Yeah, this is how it works. Another one. Oh, this is no pictures. This is the AMGC, a bit older, from 50s or 60s, and it has vacuum pumps, the vacuum chamber, lasers, sensors, dampening, and so on. Here we have some bunch of people with a lot of FG5s from different countries to be compared to each other in the same location, so their accuracy can be confirmed. This happens every year, usually. Some more. You can see it's vacuum, ion pump, laser, so on. What else do we need? This is another one in France, FG5. This is a small one. This is using MEMS. This is a different one. This is using AQG in some place. As you can see, this is put on a block of concrete. It's leveled, and then it is not connected to the building, so the vibration are removed. The blanket is because it can get very cold, so it's probably protecting that. Yeah, we can see that. Here we see another picture from another FG5. Okay, it's in many boxes, so this can be moved around to different places, and measurements can be done. Here we see a bit more of AMGC accelerometer, and this is serial number 2 with equipment. And what else? Oh yeah, these are, they made 19 machines at the time of this writing, and every year or every few years they move all together. They come by planes and ships to one place and measure at one place to see that there is no difference between them, that there is no error and calibrations are in effect. And like you can see, all of them measure the same. All bars, for example, are consistent, and this is extremely small difference between them, right? 2 - 8. So 8 decimal places, they measure the same thing to 8 decimal places. Another picture how it works, and all the influence of everything, drag, like, because this is in vacuum, so negligible outgassing, negligible temperature gradient, a little bit, but to -9, so the total effect is extremely small. All the different effects, thermal expansion, pressure, and so on, this all are measured and compared, right? It just gives you the value. The acceleration. Okay, and these are the sizes. What else? We can continue. This is again FG5 in a different location. This is some more modern one, a smaller one. Here is another one, another set of another ones. Again, FG5 and A10. Is there any picture here? Yes. Here is FG5. We already seen this image. Here is A10 in the wild to do measurements. This is a modern one, which is called CG6. These are not as accurate. These are called relative accelerometers. This is a superconducting one. This is also a relative one, much smaller. These are very recent ones. And this one is yet another one. This is using GILA.
Here is a prototype of FG5X 220. Well, it's here, and GAN in Germany, using new principles to be much more accurate than this one. This one's already super accurate, but you want to be more accurate. As every time you want more accurate, that's good. Here is a installation of one of them, of FG5s. It comes in a van. It's being installed, leveled, and then waiting for it to warm up, and then take it. This in Belgium. Another A10. Here's another FG5. This is in Finland, probably. No, in Greenland. In Kulusite, Kulusuk. And there are two of them. No, one. And they measure something, whatever. Okay. What is this? No, this is not the. Ignore that. That was not what we wanted to see. Just wrong search. Here's another one that is installed. A10 in the wild in Arizona, US. Super small. The equipment can be connected through long cable, so it's pretty easy. Do we see another one here? Another FG5. What else? What else? This one is from 83, the photo of GA60, a very big machine, as you can see. Here's how it works. Very similar pattern. There's a laser, beam, and there's free falling object in vacuum. This is FG5 again, a bit older drawing. Corner cube, spherical lens, drag-free chamber, the lift, linear detector, ion pump, and yeah, it's released and it just falls. And this is other reservoir factor, laser, and avalanche photo detector to detect things. And example of results is the acceleration and a value in meters second squared. Another FG5, different serial number. What else? Do we have any other picture? Yes, of course. This is in Leibniz. Another FG5, different model, a little bit different model, different serial number. This is GILA G3, which is older model. It's very big. What else? Do we have more? Yeah, here is a hat, I think in Japan, and there's a permanent station there, permanent equipment installed there. Maybe, yeah. This looks to be older model. Okay. Do we have any more pictures to show you? This is a relative one. This is another one in Austria, FG5 installed. Netherlands, what it says, the first. This is not between 91 99. It's more of a history, a theory, standard equation of acceleration and solutions. This is how it follows. Yeah, you can solve it, fit it. And well, these are the points that they taken in Netherlands. This is what they used in these points. They used both GILA and FG5. They even got some places built just to measure it well in many stations. And yeah, the values are here. Do we have more pictures? Yes, relative measurements. So they measured them and using some other machines to compare. Oh, we don't have pictures. So yeah, there's hundreds of them, if not thousands, around the world. And they are routinely calibrated very well. They are taken together from time to time to confirm that they didn't get decalibrated and so on. And this is just what they do. They just drop the prism in vacuum in a control environment down, and relative to the machine, you can measure the acceleration. And if the frame is bolted to the ground, sitting on the ground, you can see the what I call downward acceleration, because we can agree if we drop things either in air or in vacuum, they just fall down. But the thing is, this acceleration is different in different places. And if you repeat the same measurement many times in the same place, it is almost the same all the time. It doesn't depend what is the time of the year. It doesn't depend what is the pressure. It doesn't depend what is the humidity. It doesn't depend on pressure. Also, it doesn't really depend on the height. For example, if we sort this by height, can I do sort? I can do sort. I can do sort, and we'll remove the south poles, okay? We don't even need to look at them. Delete rows. For whatever reason. We can, but some people might be triggered. So we'll do sort. How do I sort? It's somewhere here. Sort range, and we'll sort by column E. And let's say these few results here. Let's say this one and this one. Okay, they are done basically at sea level, just a few meters above sea level. But the results are very different. You see? And if I try to find another one that is 43 in latitude, or maybe just let's find two that are at the same latitude but different heights. So let's say here, what are the differences, right? Between this one and this one. And let's divide by this one. So we have a relative measurement. And we'll say in percents. So the difference between these two measurements, which are basically at the sea level, is 0.4%. 0.4. Remember the number, 0.4. It's small, but it's there. 0.4. As you can see, it's on the fourth decimal place is different. No, sorry, the second decimal place is already different. So it's 0.40. Now, if we do sort again, but by latitude, so it's column D, and find some 2 points that have similar latitude but very different heights. So this was same height, different latitude. This was 0.40%. Now we'll do same latitude, different height. Let's see. This will be a good example, I think. Very similar latitudes. Sweden and Canada. This one is 500 meters. This is 22 meters. Can we find something higher in difference? This one is pretty good. I remember there was a Virginia city. Oh, this one is nice. These two are nice. These two are nice. Yeah, let's try that. So we'll do take this so we see all the, where was that? Oh, this might be good. Yeah, this is good. This one might be big. This one is bigger difference. Similar. So let's take this one. Equals. We'll do. Let me mark it so I don't lose it. We'll be looking at these two values. Same latitude, basically. Oh, these are both in Mexico. So maybe let's do different, completely different place. No, actually no. They're close. They're almost the same latitude. They are close together. The values should be close together, right? But does the height make a difference? Let's see. This one, let's take the bigger one first. This one minus this one. And we want relative measurement, so we divide. And take percent. So this is 0.05% difference. Okay? And let's take another one. So this is the change in height, effect of change in height in almost 2 kilometers. It's only 0.05%. But change in latitude, even at the same height, that's there's 0.4, 10 times bigger difference. So latitude has a much bigger effect. Let's take another with the same height, two or with the same height. So let's sort it again. So we'll put the 0.05% for reference, and now we'll do sort it again by height. How do you do that? Sort by height, so it's E. We want to find two with the same height, but two different latitudes. So here, this is a good one. 40 and 40, 40 meters. Okay, one in China and one in Norway. The same height, different latitudes. So what is the difference? We'll mark it here with bubble so we can see it better. We'll take the bigger one and say bigger minus smaller divided by one of them and present it as a, how you call it, percent, 0.37%. Very similar to what we've seen before. So now we'll do again, and we'll sort it by latitudes. Which is D. And find some with very different height, but same latitude. This is a pretty good one. Can we get something closer to similar values? This one, maybe. I like this one. And this one. Oh, I really like this one. Is there any other one which is even better? Oh, I think I will take this one. Or oh, this one, Virginia City. Yes, let's go this one. Oh, this is great. So we'll take Spain and Valencia in Virginia City. It is almost 2 kilometers difference in height again, but basically the same latitude. So let's do again. What is the acceleration difference between them? Bigger one minus smaller, divide by one of them, and present as percent. Again, 0.06%. 0.06%. So 0.06%. Oh. Okay. So these are basic conclusions from this data, that different heights have extremely small importance to this measurement, but different latitudes different heights introduce very little difference. Different latitudes make, even at the same height, make a very big difference to this acceleration. And again, this is what I started the last video with. To flat earthers, question to flat earthers, to flat earth people. You reject gravity, that's fine. You reject the globe model and you reject many other things, that's fine. Why this acceleration? The measurement with the devices I told you. These devices does not depend on the source of acceleration. It's just there. They give you the value. They don't care how this works. It doesn't depend on temperature. It doesn't depend on pressure. You can move them around, measure in different places, and they give you different values when you put them in different places. And my question is again, why? What is the explanation? And it's not byte question. The reason I selected this data, I mean the downward acceleration data, and gave you a bit of data here. I can go through many other data sets. We already seen some data in other documents. We can put it there, and they will be also, they need to be explained. Why this acceleration is varying? Why it's not the same everywhere? Why it is and basically not changing with height, but it's changing with latitude apparently. And also we see that very small latitudes, close to zero, the value is small. But as long as latitude is increasing, either negative or positive, the value increases. For example, here it's 983, but close to zero, it's 977. And then again, if we go high, it's again 983 or 892. So it's high at high latitudes, then it's low at low latitudes, and it's again high at negative latitudes. So what I would like to know, what is explanation, what is the mechanism for it, and I would like to have a formula that takes a position in any kind of coordinate system. It can be longitude or latitude, or it can be something else. Please give to every of the cities, give some coordinate. And then height also. If you don't agree with any of these numbers, please provide numbers for these cities and sites of location and height. And then using these three numbers, or some other numbers that I might not know about, didn't think about. Take all these numbers and get a formula that takes these three or more numbers and produces the acceleration. And the quality of the formula, it should be at least 0.1%. Yeah, the formula should be giving a result that is 0.1% within the value I gave you here. If you have a formula that is better, that's great. But if it's significantly worse, sure, you can give the formula, we can analyze it, and you can explain why it's worse. Okay, sure. Yeah, that's all. And I hope I didn't use the G word. If I use the G word, my apologies. All we are looking at is acceleration downwards. We don't care. Let's assume it is not because of the G word. It's something else. So please tell us what it is and how it behaves and how we can compute these values, predict these values. Thank you very much. Bye-bye.